Hi everyone, this session is about linear non-homogeneous recurrence relation with constant coefficients. First I will show you what is homogeneous recurrence relation and non-homogeneous recurrence relation. In the previous videos, we have seen the recurrence relation of the form an is equal to 3 into an minus 1. So here it is linear and as well as homogeneous. So it is linear homogeneous recurrence relation. And suppose if you take the recurrence relation an is equal to 3 into an minus 1 plus 2n. So here earlier we have plus 0 but here we have plus 2n. So that this term is not in the format of ck into an minus k. So it is non-homogeneous. So here I am introducing a new term called associated homogeneous recurrence relation. So associated homogeneous recurrence relation means if you see here up to this one is called as associated homogeneous recurrence relation. So for this one an equal to an minus 1 is the associated homogeneous recurrence relation. For the next one an is equal to an minus 1 plus an minus 2 is the associated homogeneous recurrence relation. And for the next one an equal to 3 into an minus 1 is the associated homogeneous recurrence relation. For the next one an is equal to an minus 1 plus an minus 2 plus an minus 3 is the associated homogeneous recurrence relation. The linear non-homogeneous recurrence relation with constant coefficients is in the format of C0 into an plus C1 into an minus 1 plus C2 into an minus 2 plus and so on plus ck into an minus k is equal to f of n. So for non-homogeneous recurrence relations, f of n is not equal to 0. For homogeneous recurrence relations, this f of n is 0. The solution for this non-homogeneous recurrence relation is an is equal to anh plus anp. So anh here is homogeneous solution. So we have seen in the previous videos, this is homogeneous solution plus ANP is particular solution. This homogeneous solution is same as the previous videos, but we need to learn about how to calculate this particular solution. So this homogeneous solution is coming from the associated homogeneous recurrence relation. So this is nothing but the solution of associated homogeneous recurrence relation. The first example we are going to see is an minus 7 into an minus 1 plus 10 into an minus 2 is equal to 3 power n, where a0 equal to 0 and a1 equal to 1. This is a linear non-homogeneous recurrence relation because here f of n is 3 power n. The solution for this is anh, that is homogeneous recurrence relation, plus anp, that is a particular solution. anh, that is homogeneous recurrence relation solution, is nothing but the solution of associated recurrence relation. Associated recurrence relation is an minus 7 into an minus 1 plus 10 into an minus 2. Let an is equal to r power n is the solution. As we have seen in the previous videos, we are solving the homogeneous recurrence relation solution. So here it is r power n minus 7 into r power n minus 1 plus 10 into r power n minus 2. So here we need to divide with r power n minus 2 so that we are going to get r square minus 7 into r plus 10. So now we need to find the roots for this. So we can write it as r square minus 2r minus 5r plus 10. So this can be written as r into r minus 2. Here we can take minus 5 as common, r minus 2. So we can write it as r minus 2 into r minus 5. So here the roots are 2 and 5. These two are distinct roots. And one more thing is f of n is equal to 3 power n. And these two are not at all matched with the 3. So here the roots are 2 and 5. These are not matched with the f of n, that is 3 here. So this is the case 1 type of problem. ANH, that is homogeneous solution, is alpha into 2 power n plus beta into 5 power n, since the roots are distinct. And for the particular solution, that is ANP, is a into 3 power n. So here I am going to discuss some table which is important. Based on that, roots are distinct and f of n is 3 power n and any of the root is not matched with 3. So the solution is a into 3 power n. Suppose if the root is 3 and function is 3 power n, 3 is matched and the multiplicity is 1. So then the particular solution is a into n 3 power n is the solution, particular solution. Suppose root equal to 3, 3. There are two roots, both are 3 and the function is f of n is 3 power n. So here it is 3, here it is 3 and the function is also 3 power n. So the multiplicity is 2. So here the multiplicity is 2 and here the multiplicity is 1 only. So that's why we have kept n power 1. Here the multiplicity is 2. So the solution is a into n square 3 power n. Coming back to the original problem, here the roots are 2 and 5 and the function is 3 power n. That means it is comes under the category roots are distinct and it is not matched with the function 3 power n. So the solution is a into 3 power n. Now we are going to substitute this particular solution in the original recurrence relation. So now in place of an, we are going to place a into 3 power n. So we are going to get a into 3 power n minus 7 into an minus 1 means a into 3 power n minus 1 plus 10 into a into 3 power n minus 2 is equal to 3 power n. Solving this one, we need to get the value of a. So we can write it as a into 3 power n minus 7 into a into 3 power n divided by 3 plus 10 into a into 3 power n divided by 3 square. 3 square I can write it as 9 is equal to 3 power n. If you take a into 3 power n as common, we will get 1 minus 7 by 3 plus 10 by 9 is equal to 3 power n. We are further simplifying as a into 3 power n. If you simplify this one, we are going to get minus 2 by 9 is equal to 3 power n. And we can cancel 3 power n here and we can imagine, right, into 1 here. So here it is 1 is there. So minus 2a divided by 9 equal to 1. So a equal to minus 9 by 2. If you substitute in the particular solution, so a and p is equal to a value is minus 9 by 2 into 3 power n. So this is the particular solution. Now the final solution is a n of h plus an of p is the final solution. Alpha into 2 power n plus beta into 5 power n plus an of p is minus 9 by 2 into 3 power n. This 9 can be written as 3 square, so that 3 power n plus 2 by 2 we can write. This is the final solution for the linear non-homogeneous recurrence relation with constant coefficients. So in the given problem, A naught is equal to given as 0, alpha into 2 power 0 plus beta into 5 power 0 minus 3 power 2 divided by 2 is equal to 0. So we are going to get alpha plus beta minus 9 by 2 is equal to 0. And one more thing given is a1 equal to 1. So we are going to substitute 1 in place of n. So plus beta into 5 power 1 minus 3 power 1 plus 2 divided by 2 is equal to 1. So we can write it as 2 alpha plus 5 beta minus 3 power 3 is 27 divided by 2 is equal to 1. So this is equation 1 and this is equation 2. By using these two things we can calculate alpha and beta. So 2 alpha plus 5 beta is equal to 1 plus 27 divided by 2. So this is 29 by 2, and so the equation is 2 alpha plus 5 beta is equal to 29 divided by 2. We are multiplying equation 1 with 2 on both sides. So we are going to get 2 alpha plus 2 beta is equal to, so 9 by 2 we are multiplying with 2, so 2 into 9 by 2, so 2 cancel, and if you subtract 2 alpha minus 2 alpha will be cancelled, and 5 beta minus 2 beta, it is 3 beta is equal to 29 divided by 2 minus 9 by 1. So it is 29 minus 18 divided by 2. So it is 11 by 2. So this is 3 beta. So beta equal to 11 by 6. Then we can calculate alpha. Alpha is equal to 9 by 2 minus beta. Minus beta is 11 by 6. So we got alpha equal to 8 by 3. So the final solution is an is equal to, so alpha is 8 by 3 into 2 power n plus beta value is 11 by 6 into 5 power n minus 3 power n plus 2 divided by 2. This is an example for if the roots are distinct and the roots are not matched with the function f of n. If f of n is a polynomial, how to find the solution, all those things we can see in the next video. Please do subscribe and thank you for watching.